There is a number in physics so precise it should not exist. Not very precise, not surprisingly precise. A number tuned to 1 part in 10 to the power of 120. And if it were off, even by a fraction so small no unit of measurement has ever been invented to describe it, there would be no galaxies, no stars, no planets, no you. Physicists have a word for numbers like this. They don't call it a coincidence. They call it a problem. And for 50 years, nobody has been able to explain why it isn't one. Let's start with something you can hold in your hand. Take a coin, flip it, heads or tails, 50-50, and you don't think twice about it. Now imagine flipping that coin and it landing on its edge, balanced perfectly upright, not once, but every single time for 120 flips in a row. You would not call that luck. You would assume the coin was rigged. You would assume something or someone was holding it there on purpose. That's not a metaphor for something abstract. That's the actual state of the universe, measured, confirmed, published in peer-reviewed journals, and mostly ignored by everyone who isn't a cosmologist. The universe has been standing on its edge since the first fraction of a second of its existence, and nobody can tell you why it hasn't fallen over. Here's what that actually looks like in numbers you can picture. Imagine the mass of every atom on planet Earth. Every ocean, every mountain, every living thing, every grain of sand, all of it added together. Now, imagine trying to weigh the entire planet on a scale so exact that if you were off by the mass of a single atom, just one, out of that entire planetary total, the scale would register an error. Hold that image. That's roughly 1 part in 10 to the 27th. Precise enough to sound impossible already. Now here's the part that should actually bother you. The number this video is about is not that number. It's 100 orders of magnitude beyond it. If weighing the Earth to the mass of a single atom is impossible precision, the number we're talking about is that same task, repeated, with the bar raised 100 times over. There is no object in your imagination big enough to build an analogy that fully captures it. You just have to sit with the fact that it's bigger than anything you can picture, and it's not a theory, it's a measurement. So why does this number exist? Why is the universe balanced on an edge sharper than anything in your imagination? Stay with this because the answer splits into 4 possibilities, and every single one of them is stranger than the last. To understand where the number comes from, you have to understand what physicists call flatness. Picture the universe as a sheet, not physically flat like a piece of paper, but geometrically flat, meaning if you sent 2 parallel beams of light out into space, they would travel forever without ever converging or diverging. That flatness depends on a single value called omega, which measures the total energy density of the universe against a specific critical threshold. If omega is greater than 1, the universe curves back on itself like the surface of a sphere, and eventually collapses under its own gravity. If omega is less than 1, the universe curves outward like a saddle, and expands so violently that matter never has the chance to clump together into anything. Omega has to sit almost exactly at 1 for a universe to produce stars, galaxies, chemistry, or life. Not roughly 1, not approximately 1, practically, indistinguishably, terrifyingly close to exactly 1. Here's where it gets stranger. The universe we live in has been expanding for nearly 14 billion years, and today, after 14 billion years of any tiny imbalance compounding and magnifying over time, omega is still sitting at almost exactly 1. Run the math backward, and that means in the earliest fraction of a second after the beginning, before atoms, before light could travel freely, before anything we would recognize as physical reality, omega had to be tuned to a precision of 1 part in 10 to the power of 60. Some models push it further. Trace the compounding effect all the way back to the very first instant, and the required precision reaches the number we opened with. 1 part in 10 to the power of 120. That's the coin. That's why it's still standing on its edge, 14 billion years later. But here's the thing nobody tells you when they explain the flatness problem. Flatness is only one dial. It is not the only place the universe had to land on a razor's edge. And once you see the second one, the first one stops looking like an isolated fluke. There's the cosmological constant, the strange background energy of empty space itself, measured at roughly 10 to the power of negative 122 in natural units. Sit with that number for a second, because it deserves more than a passing mention. If that number were even slightly larger, the repulsive force of empty space would have blown matter apart before gravity ever had the chance to pull it into stars. Not damaged the process, prevented it entirely, permanently, before a single star ever formed. If it were slightly smaller, the universe would have collapsed back into itself within the first second, before time had anywhere to go, before there was even a before for anything to happen in. 2 Nobel Prizes have been awarded to scientists for measuring pieces of this puzzle. Neither prize came with an explanation for why the numbers landed where they did. The committee handed out the award for confirming the mystery, not for solving it. This isn't a number someone went looking for and got lucky finding. It's the opposite. The measurement kept coming back so absurdly small that for years, physicists assumed it had to be exactly zero, because a number that close to nothing, without actually being nothing, seemed too strange to be real. It took satellite data, distant supernovae used as cosmic yardsticks, and years of independent confirmation before the scientific community accepted that the number wasn't zero. It was just almost zero, in a way precise enough to look deliberate. And it doesn't stop there. There's the ratio between the strength of gravity and the strength of electromagnetism, which has to be tuned to roughly 1 part in 10 to the 36th for stars to form and burn steadily instead of collapsing into black holes or flickering out in an instant. Push gravity even slightly stronger relative to electromagnetism, and every star that ever formed would have burned through its fuel in a matter of years instead of billions of years, meaning no planet would ever have had time to develop life, let alone anything capable of asking why. There's the mass of the electron, tuned within a narrow window that allows atoms to bond into molecules instead of falling apart or fusing uncontrollably the instant they touch. Move that number even slightly, and chemistry, all of it, every reaction that makes a body or a brain or a breath possible, simply doesn't happen. To put that ratio in a picture instead of an exponent, imagine gravity as a single grain of sand, and electromagnetism as a beach, stretching far enough to circle the planet several times over. That's roughly the gap in strength between the two forces. And yet, the two of them had to be tuned against each other with enough precision that stars could hold themselves together against their own gravity, burning slowly for billions of years, instead of collapsing instantly or drifting apart before they ever ignited. Change the size of that single grain of sand by an amount too small to see, and every star in every galaxy either never lights up or burns out within a human lifetime. Stack these constants side by side, and something changes about how you have to think about this. You don't get one improbable number anymore. You get a chain of them, each one measured independently, by different instruments, in different decades, by scientists who weren't looking for a pattern and weren't trying to prove anything about God or design. And every single one of them landed exactly where it needed to for anything to exist at all. Ask yourself honestly, at what point does a coincidence stop being a coincidence and start being a pattern you have to explain? Physicists have a name for this whole uncomfortable situation. They call it fine-tuning. And they have spent decades trying to explain it away without invoking anything that sounds like intention. There are 4 serious attempts, only 4. And once you understand all 4, you'll understand why this question refuses to go away. The first attempt is called inflation, the idea that the universe underwent an unimaginably fast period of expansion in its first fraction of a second, stretching out any initial curvature until it appeared flat, the same way the surface of a balloon looks flat if you're standing close enough to it. Inflation is elegant. Inflation is mathematically consistent with several independent lines of evidence, including patterns in the cosmic microwave background that were predicted before they were observed. It's one of the most successful ideas in modern cosmology. But here's the catch, and it's the part most explainers leave out. Inflation doesn't remove the fine-tuning problem. It relocates it. Because for inflation to produce a flat universe, the initial conditions that trigger inflation, the specific properties of the field that drives that expansion, have to themselves be tuned within an extraordinarily narrow range. You haven't solved the coin balancing on its edge, you've just built a machine that's supposed to balance it for you, and the machine itself needs to be built with the same impossible precision you were trying to explain in the first place. It's a beautiful answer that quietly asks the same question again, one level down. So if inflation just moves the mystery instead of solving it, where else can you turn? The second attempt is the multiverse. If there are an infinite number of universes, each with randomly assorted physical constants, each one a different roll of the dice on omega, on the cosmological constant, on every dial we just walked through, then somewhere in that infinite ensemble, a universe like ours, flat, stable, capable of producing stars and chemistry and creatures who ask questions about it, was bound to appear eventually. In an infinite lottery, every ticket wins somewhere, and we simply happen to be standing inside the ticket that won. This is a real, serious position, held by respected physicists at real institutions, not a fringe idea from the internet. But it comes with a cost that rarely gets mentioned in the popular explanation. The multiverse is, by its nature, unobservable and untestable. There is no experiment, no telescope, no measurement, currently or perhaps ever, that can confirm or deny that other universes exist outside our own. It solves the fine-tuning problem by proposing something that cannot, even in principle, be verified. You trade one mystery, why is this universe so precisely tuned, for a bigger one, an infinite number of unobservable universes you have to simply take on faith. Read that sentence again. Take on faith. In a solution proposed specifically to avoid religious language, there's a version of the multiverse argument that tries to dodge this problem, called the anthropic principle. It goes like this. Of course we observe a universe fine-tuned for life, because if it weren't fine-tuned, there would be no one around to observe it. Only the universes capable of producing observers get observed. It sounds airtight the first time you hear it, but sit with it a little longer and a crack appears. The anthropic principle explains why we, specifically, find ourselves in a life-permitting universe, assuming other universes exist. It does not explain why a mechanism generating other universes exists at all, or why that mechanism itself is built in a way that occasionally produces universes like this one instead of nothing, ever, anywhere. You've explained the selection. You haven't explained the deck the cards were pulled from. Hold on to that distinction, because it's the difference between answering a question and renaming it. The third option is the one most textbooks are careful to avoid saying out loud, because it isn't really an answer. It's a refusal to keep asking. That the universe simply is what it is, that these numbers just happen to be what they are, full stop, with no deeper explanation available or perhaps even possible. This is sometimes called a brute fact. Some physicists find this position entirely reasonable, arguing that at some point, every chain of explanation has to end somewhere, and there's no reason it can't end here. Others find it deeply unsatisfying, a scientific shrug dressed up as an answer, a way of closing the question by declaring it closed rather than by actually resolving it. And then there's the fourth option, the one that makes physicists visibly uncomfortable in interviews, the one that shows up in footnotes and gets quietly walked back in the very next paragraph. That the precision itself is evidence of intention. Not proof, evidence. The kind of evidence a detective would take seriously if they found a room where every single object was placed with exact, deliberate purpose, and the only explanation on the table was, it happened to land that way. Here's what makes this different from a religious argument dressed up in science, and it matters that you understand the difference. Nobody in this conversation is claiming to know what set the dial. Nobody is claiming to have measured a designer, or detected a purpose, or proven a plan. What they are pointing at is much narrower and much stranger. The measured value of a fundamental physical constant, arrived at through instruments, through mathematics, through the most skeptical peer review process human civilization has ever built, keeps landing in the impossibly narrow window required for anything to exist at all. That fact is not up for debate. It's been measured, checked, and measured again. What it means, that's the entire argument, and it's an argument physics itself cannot finish. Think about where that leaves the four options, side by side. Inflation, which explains the fine-tuning by requiring its own fine-tuning. The multiverse, which explains the fine-tuning by proposing something that can never be observed. Brute fact, which explains the fine-tuning by declining to explain it. And intention, which explains the fine-tuning perfectly, but only by introducing a question physics was never built to answer. Notice something about that list. Every single option costs you something. There is no version of this where you get to keep a fully self-contained, fully explained universe with nothing left over. You either accept infinite, unobservable universes, or an unexplained coincidence stacked on unexplained coincidence, or a machine that needs its own explanation, or a designer nobody can locate. Pick your mystery. There isn't a version of this conversation where you leave without one. This is worth sitting with, because it's rare in science. Usually, more data closes a question. You measure something, the uncertainty shrinks, and eventually the mystery resolves into an answer. This is the opposite. The more precisely physicists measure these constants, the sharper and stranger the coincidence becomes. 50 years ago, the fine-tuning problem was a rough observation, easy to wave away as an artifact of incomplete measurement. Today, with satellite data, particle accelerators, and decades of independent confirmation, the numbers have only gotten more exact, and the precision has only gotten harder to explain. This is not a gap in knowledge that's closing. It's a gap that's been measured more carefully and has stayed exactly as strange. Some physicists look at the number and see the multiverse, and they sleep fine at night. Some look at it and see inflation, elegant but self-referential, and they consider the matter closed enough for now. Some look at it and see a brute fact, the universe simply being the way it is, requiring no further explanation, in the same way you don't ask why numbers add up the way they do. And some look at that number and feel something they're not supposed to feel while wearing a lab coat. They feel that they're looking at a room that was arranged, not found. Nobody can prove which of these is correct. That's not a failure of physics. That's the honest edge of what physics, right now, today, is capable of telling you. The instruments are precise enough to measure the tuning, down to 120 decimal places. They are not precise enough, and may never be precise enough, to tell you why the tuning exists. So here's where that leaves you, sitting wherever you're sitting, made of atoms that could only exist because a number balanced on an edge sharper than anything you can picture. In a universe that has been standing upright since before light could travel freely, for reasons nobody has ever been able to close the loop on. Every measurement your phone relies on, every satellite that tells it where you are, every calculation that put a spacecraft on the surface of another planet runs on the same physics that produced this number. This isn't a fringe idea living in the margins of the field. It's sitting in the center of the same body of knowledge that built the modern world. Unresolved, unavoidable, and quietly waiting for anyone who bothers to look closely enough at the numbers to notice it's there. Was it inevitable? Was it one outcome among infinite others, and you simply happened to be asking the question from inside the winning universe? Or was it arranged? Nobody can tell you. Not yet. Maybe not ever. And the strangest part of all of this isn't the number. It's that you exist long enough and are curious enough to have noticed it was there at all.